The last lecture was about classical chaos, and we discussed a simple model, Baker's map. And today I want to introduce quantum chaos and discuss another simple model, which is bacterial growth or curator growth. It turns out that the Heisenberg evolution of an operator and the chaotic system is similar to the growth of a bacterial colony. This is also a classical picture, and in the end of the lecture, I'll show you the SYK model, which we'll discuss later. And the SYK model is a model that covers a corner not covered by these classical models. Basically, quantum mechanics is ultimately important in certain cases. And the SYK model is a good model to describe quantum effects in chaos. So let's start with a semi-classical system. It's basically a Hamiltonian system with some variables x1 through x2n.
Sorry, it's better to use the other.
Yeah, it's almost invisible. Can you please use the other one? Any.
Yeah. So x q1 q1 qn. And this x evolves in time. And we can calculate the derivative of xj of t over dxn of 0. And this quantity under chaotic evolution grows exponentially. And this is the general expression. Anyway, let's postpone this calculation. Let's just draw a picture. This is some Q, this is some P. Different Q's and P's have different natural scales, but we may assume that Q and P varies from, say, 0 to Q star, and P varies from 0 to P star. And we start from some point x of 0. There is a trajectory that arrives at x of t, and if we start at a nearby point, then it will be x tilde. Now, in quantum mechanics, there is an uncertainty in the position and momentum. So one can assume that there is a wave packet that can be localized to some degree in Q and in P, but there is always some uncertainty. Delta X, delta Q, delta P is of the order of the Planck constant. And when this system evolves, not only these points diverge, but also the wave packet evolves correspondingly. So the wave packet becomes like this, and eventually the uncertainty in one of the directions can exceed the range of Q and P. And that is the point where quantum effects become important, and the corresponding time is called the Ehrenfest time. So it's given by this estimate. If this thing is proportional to e to the kappa t, kappa is the Lyapunov exponent, then we can write e to the kappa times the Ehrenfest time is of the order of U star, E star over H bar. Assuming that the shape of this wave packet is optimally chosen, such that it stretches and squeezes roughly by the same amount in Q star and in Q and P. So this is the Ehrenfest time, and it should be compared to the Heisenberg time, which is 1 over the energy level spacing. And one can argue that in an n-dimensional system, this quantity scales like U star, P star over H bar raised to power n minus 1. And in a many-body system, this time is much longer than that. So we're focusing on the behavior of the system at shorter times, and don't care about the behavior at very long times. Now, if the time is of the order of the Ehrenfest time, we need to develop some tools to quantify the behavior of the quantum system. And we want to construct a quantity that is similar to that. And a natural quantity is called an out-of-time order correlator. Such correlators were introduced by Larkin and Ovchinnikov more than 50 years ago. And I'll tell you their motivation for introducing such correlators. It's quite different from what I'm doing right now. So, let's calculate this quantity using the fact that x of t is obtained from x of 0 by a canonical transformation, the symplectic method. Then we can relate this quantity to the Poisson bracket between xj of 0 and xm of t, which is and as we discussed, this scales as e to the kappa t. In quantum mechanics, the Poisson bracket is analogous to the commutator. So the commutator of quantum observables scales as h to the e kappa t. However, this is just an operator, not a quantity that is directly measured or calculated. To construct a suitable quantity for calculating it in a certain model, in a particular model, we can do two things. We can square this number, this operator, and take its expectation values over some states. For example, the thermal state. And this expectation value will scale as e to the 2 kappa t with a small coefficient. But we can also do something like this. And we can compute the expectation value with just the product of two operators. And this will scale just as h e to the 2 e to the kappa t. Now, if we extend the commutator, there will be two terms. One term where the times alternate, and the other term where the zero time is next to this zero time. And the second type of operator doesn't grow in time, if we compute the expectation value. Only the operators with the expectation values with alternating times grow. And so we can focus on calculating autops out of time order correlates.
Shouldn't it be h bar squared exponent of kappa t in the last one?
Here, h bar squared. No, here it's proportional just to h bar. The commutator is a small number. In classical mechanics, observables commute. In quantum mechanics, they do not commute, but the commutator is small. It's proportional to h bar. Here we use the commutator twice, and in this expression we use the commutator once. So.
But on the other hand, this lower line seems to be just a piece of square commutator.
Right. That is correct. There are other factors. That's why I write proportional to. So if we there is some factor in front that doesn't contain h bar. Now, if we express this quantity in terms of general out of time order correlators, let me write down the general expression first. It looks like A of 0, C of t, B of 0, D of t. There is one pair at time 0 and another pair at time t. And obviously, this expression is a sum of 4 terms like that. But there is an almost cancellation between those terms. This quantity is much smaller than that quantity, where nothing counts. Actually, there is some cancellation, because if we just yeah, I take it back. Okay, now I can answer your question more exactly. Let's write down all 4 terms here. So. And there are 2 more terms, 4 terms total. This quantity, in general, is of the order of 1, and that is also of the order of 1. So all the terms are of the order of 1. Now, let's consider the case where t is actually less than interest time. Such that the semi-classical analogy is applicable. Then this number, h bar times e kappa t, is much less than 1. Or rather, this commutator is much less than 1, because there is an extra factor here. There is a partial cancellation between these 2 terms. When we subtract them, we get something proportional to this, which is much less than 1. If we consider all 4 terms, there will be more cancellation, and the result is even smaller. It's quadratic in each part. Yeah.
Could you repeat the full name of Ocho?
Out of time order correlator. Let me write it down. So this argument is applicable to early times when this quantity remains small. At the Ehrenfest time, this quantity is of the order of 1, and then it becomes formally much greater than 1, but then this analysis is not applicable, because one has to solve the quantum problem rather than the semi-classical problem. So if we plot or top as a function of time, we can use some assumptions. We may assume that A has zero expectation value, and the same for B, C, and D. Then we can consider this quantity at short times and at long times. At t equals 0, this number has some value. And at t equals infinity, this quantity actually goes to 0. One can show that it approaches 0 if the expectation values are all equal to 0. And there is some intermediate time t that is much greater than the inverse Lyapunov exponent, but much less than the Ehrenfest time. And first there will be some evolution of this quantity to this intermediate time value. Actually, it's called early time value. And then there will be some further evolution. And let's look at this difference. So it's and this quantity scales as h bar e to the kappa t. If t is much less than the Ehrenfest time, and much greater than kappa to the minus 1. So this exponential growth is only applicable to a certain range of times, actually a very narrow range of times, because there is this logarithmic function. And that's where the semi-classical approximation is applicable. We'll not consider semi-classical systems, we'll consider Lagrangian systems, in particular the SYK. So I'm not very careful about this stuff. In the SYK model, there will be a proper derivation of this behavior. But let me discuss the general context where such out-of-time order correlators occur. The first observation is they don't appear in naturally forced problems. It's kind of artificial. It means the following, that when we consider the natural evolution of a quantum system in time, then we start with some density matrix, and that density matrix is usually the thermal density matrix. Then the system evolves according to some Hamiltonian, and it can be the Hamiltonian of the system itself, or we can introduce some apparatus during this evolution. We can control the evolution of the system, applying a perturbation to the Hamiltonian. And at time t, we perform some measurement. And this way, we have access to certain correlation functions of the system. By doing different measurements, we can measure different correlation functions. So, natural correlators or Keldysh correlators look differently from this stuff. So let's start from some density matrix rho 0. Say is the thermal density matrix. And then we introduce an evolution operator. And it can be written in the interaction representation like this. It's the time-ordered exponential of and the quantity we can measure experimentally is given by the trace of rho times some operator, say z of t, evolved by the evolution operator. And if we expand u in the perturbation and expand u minus 1 in the perturbation, then the order of operators corresponds to the Keldysh contour. So this is t. the operator order corresponds to the contour order. For example, we can have 4 points, T1, T2, T3, T4, and the expansion contains this term. And the expectation value means this trace with the sum of density matrix. So the times first grow and then decrease. An out-of-time order correlator never appears in this setting. And I mentioned that the out-of-time order correlators were introduced by Larkin and Ovchinnikov. And that was more than 50 years ago, and back in those times, it was strongly discouraged to consider programs not related to experiment. So they wouldn't have considered this program just for the sake of it, because it's extremely difficult to arrange this measurement, not this one, but the measurement of this quantity. I'll mention how it can be done in principle, but it's very difficult, and it is only possible for small systems. But Larkin and Ovchinnikov was motivated by a different problem. They were calculating some superconducting response, actually a static response of a superconductor in the fourth order of perturbation theory. Which is related to correlation functions of 4 current operators. And they reduced the correlation function for the superconductor to the correlation function of the corresponding normal metal. Because superconductivity in the BCS model is related to the normal metal in a very simple way. And it turns out that normal correlators of the superconducting currents can be expressed in terms of out-of-time order correlators for the normal metal. And that was their motivation. They didn't try to study times. It just occurred accidentally. But going back to a possible scheme of measuring such a correlator, there are essentially 2 ways to access it. And the same actually is true for classical chaos. To observe classical chaos not in a simulation, but in a real system, one needs to either have a reference copy of the system, such that the evolutions of the same system with different boundary conditions could be compared. Or one should have the ability to run time backward. So either this or that. And I don't know of a better way to perform a measurement of chaos. Speaking of a quantum system, it is actually possible to reverse the time evolution on very small systems made of qubits. And another example is nuclear spins in molecules, accessible via NMR, nuclear magnetic resonance. In this case, there are tricksome pulse sequences that effectively reverse the evolution. So I say the evolution is driven by dipole-dipole interaction between the spins. One cannot change the dipole-dipole interaction, but one can arrange some sequence of pulses such that the dipole-dipole interaction over a certain period effectively cancels the same evolution over the initial period. And what's left is the out-of-time order correlator. So one way to measure out-of-time order correlators is to run the Hamiltonian evolution backward. And another way is to have a reference copy of the system. And a reference copy would be a thermal double. So if we use the thermal density matrix, we can consider the state psi, which is roughly the square root of rho z. What it means is we can write rho 0 as a sum over eigenvalues of the Hamiltonian. And here we can write z to the minus 1/2. It's a system that consists of two parts, and in principle, there can be states like J and K in the two parts, but the Thibodeau double only contains pairs with equal labels, n and n. And the density matrix can be obtained as the partial trace over subsystem 2 of psi sum.
Excuse me, you don't need the drop in your side. Size of your state. Size of your state. You don't need the drop.
You have some projections.
Here,
To the right, yes.
Right. It's just,
Yeah, that's right, it's not that.
that is not there.
no, well, actually, direct notations are not very suitable for this kind of tricks. Yeah, mathematicians usually don't use direct notation because they do more general things than physicists do. This is one example. Here we're reinterpreting a Bragg vector as a ket vector of a different system.
Yeah, but you need 4. We need just 2.
Here,
The drop, the second factor is
well, how do I change it?
I would just write n because it's just 2 radicals. So this is the right.
You have to erase the rightest part. Just
Oh,
erase. Yes.
yeah. Sorry, I was already thinking about this part. Yeah. Yeah, sorry. Yeah, thank you. Right. So I meant this thing when writing the previous expression. But in this setting, we can start with the Sommerfeld double. Let me draw a picture, this time going vertically and use colors. Here, there is no coordinate, it's just then we can apply some operators on the left and on the right, and we can perform a measurement, and this measurement will be a joint measurement. So but to calculate a probability out of this measurement, we need to flip the picture about the horizontal line. We need to combine the cat vector with the corresponding bra vector. And now, if this is applied at time 0, this is applied at some time t1, and that is again applied at time 0. Taking the expectation value involves multiplying those operators around this loop. And you see that the times alternate. They go between 0 and t1. So this is a different scheme where we use a reference system.
But what are these G and W?
These are some operators that we measure. So we start with SYK. Then we apply x and y at time 0. And x is applied to the left system, and y is applied to the right system. At time t, we perform a measurement, and this is a joint measurement, where we're measuring the product of operators z and w applied to different systems. For example, it can be, if it's a spin system, we can do the simultaneous projection onto as z equals 0 in both subsystems. So and the probability that the measurement outcome is positive, I mean, it gives the answer yes. Both spins have zero projection onto the z-axis. will be given by this expression. And here it's the SYK. And so, as an example, we can and this matrix element of the double system is related to a matrix element, or rather the trace on a single system. And the rule is this: we replace psi by the square root of rho 0. And whenever we have an operator like this, something acting on the left and something acting on the right, we literally multiply by x on the left and y on the right. Then we multiply by z and w similarly. And then we multiply by x dagger, y dagger. And then we take the trace with psi, which means trace of this operator times the square root of rho 0. It's slightly different from the top because instead of rho 0 in one place, we have a square root of rho 0 in two different places. And I would say it's a different formula too. So, yeah.
Can you please explain once again what are x, y, z, w, and how in the end of the day this formula gives us like this logical operation?
Yeah, sure. So let's set up an experiment. And actually, this kind of experiment has been done by Google using the quantum processing. So the experiment looks like this. We created a thermophile double state. For example, it can be the infinite temperature state, where rho 0 is proportional to the identity operator. But then, at time t equals 0, we simultaneously apply some operator x to the left subsystem and some operator y to the right subsystem. Let me just write down the protocol and you can relate it to the picture. And those subsystems are called L and R.
Sorry, may I ask another question?
Yeah.
Right now. So those are actually subsystems, or they are just like states in which our system can be? either in left, either in right?
No, these are subsystems.
Subsystems.
It's a double system.
Okay. And each, so just for me to understand correctly, and in the incoming temperature approximation, we assume that the system can be in any state in any of these subsystems. Okay.
Yeah. So this is time equal to 0. Measure some joint operator and joint observers. Just the tensor product symbol, but it's redundant because we already have labels L and R. And to make full match, let me just change the label. This is time. So this is the protocol. The expectation of the measured quantity is given by this expression. And
between time, in the time branch between 2 and 3, two systems evolve independently, left and right systems.
yeah, they evolve independently.
A continuation of the previous question. When in reality they will decohere, so the subsystems will somehow lose the coherence between each other. And what's the practical implication of this decoherence on the actual interpretation of the measurement result? So what I will measure instead of the true out-of-time correlator?
Right. This is an important question. If there is decoherence, it will spoil the result very badly. Basically, it's a stress test for a quantum computer. Suppose we have 100 qubits, we evolve the system for 100 steps. Modern quantum devices cannot do that. It's just too much. But suppose we have a better device. If there is a single act of decoherence in that whole process, which involves, say, 10,000 gates, then everything is destroyed.
So
And so we should make our device almost perfect to measure it.
And an alternative approach would be just to use the fact that in the device we just can apply directly U and U dagger. That's why we can evolve forward and then formally backward. And then the coherence problems is not that severe, right? And we simply exchange the depth of the circuit, which is smaller here, for the fact that the effect of the coherence is much more severe, right?
I think there is no escape. Whatever you do, you'll be susceptible to decoherence.
Yeah, but you're saying that here it's completely catastrophic, and in this more straightforward experiment, it's maybe...
I think it's always catastrophic.
Okay.
So it's actually a fundamental thing. To measure chaos, we need to do something very sensitive. And that's why chaos is studied theoretically rather than experimentally. At least it has been studied theoretically until recent times. Now people do low-Schmidt echo using NMR and this kind of thing using a quantum computer. But there is something interesting. Recall that Larkin and Ovchinnikov discovered out-of-time autocorrelators studying a natural correlator of 4 currents. This is because the Cooper pair is somewhat like this state sign, bipartite state. It's a single particle version of it. And a natural question would be, can one construct a many-body analog of a Cooper pair? And there is actually a construction that starts with the SYK, which we'll start discussing next time. And there is a Malvesson G model. Which is 2 copies of SYK, coupled to each other. And due to this coupling, a state is formed that is similar to the Sommerfeld double state. But unlike the Sommerfeld double state, it's much less sensitive to decoherence. And various things that can be said about the SYK model and out-of-time autocorrelators in the SYK model are related to natural correlators in the Malvesson-Chi model. So it's not completely impractical exercise to study out-of-time autocorrelators because in the end we can relate it to something more easily measurable than out-of-time autocorrelators.
Another question. How much different is this correlation function from the first version of out-of-time order where you have just one-density matrix instead of squares?
At infinite temperature, they are the same. At finite temperature, they are obviously different, and there are some relations between them. One can derive some identities using various assumptions. And I would say that both variants are valid, and one can construct a more general variant where different powers of rho 0 are inserted in all possible places here. And one can calculate such a general correlation function. Unfortunately, I cannot say that one correlation function is the right one and the other is not the right one. One has to calculate those formal expressions separately, or as a special case of some general expression. So, let's talk about semi-classical chaos in spin systems. And we consider the infinite temperature case. The Hamiltonian can be the Heisenberg Hamiltonian for a spin chain, or it can be some other Hamiltonian. And the main idea in the study of chaos and infinite temperature is to use a representation of operators as quantum states. So if we have some operator A acting on the system, we can represent it as a quantum state. And we have previously used this trick. We have converted this curve over 0 into a quantum state, psi. But in general, the trick is this. We can formally consider operators like A and B and form a Hilbert space by introducing an inner product. And the inner product between B and A will be d to the minus 1 trace the B over A where D is 2 to the 2n, and n is the number of states. So this is an abstract construction. We treat an operator as a vector. We can do it more concrete. We can say that given an operator A, we form the vector ket A
Yeah, the top edge.
There's
yeah, that's the other way around. Suitably normalized. We can we should introduce a normalization factor here. Now, why is it useful? Let's consider an expression like and this is if we look at these operators in the correlation, we can express them in terms of sum operators at time t. So we can kind of push them forward to time t using the Heisenberg equation. So we can write an expression for a I would prefer to just use this one because I cannot push it with the low board to the top. So let me just do a long calculation on blackboard. So the operator at time zero is expressed in terms of sum operators at time t. And this is a Pauli operator where A is a sequence of A1 through A to the n, and A sub j can be 0, x, y, z. These are just labels. They don't have numerical values. These are just labels. And that means that there are Pauli matrices like sigma 0, which is the identity, and sigma alpha, where alpha is x, y, z. And sigma A is just sigma A1 tensor dot 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 sigma A1. So I'll call A Pauli string. And now we're moving this operator in time. Let me first write the general equation, and then I'll illustrate it using a particular example. This is the Heisenberg equation. It's I H and we can write it down as I there is some effective Hamiltonian curly H. And this effective Hamiltonian changes one Pauli string to another Pauli string. For example, let's consider just two spins, and the Hamiltonian will be minus j over 4, just the Heisberg interaction between the two spins. And if we can use the Hamiltonian with sigma, I'm using a particular Pauli string, 0x, and that is sigma 0 times of sigma x, which is the same as sigma x acting on the second spin. If we calculate the commutator, then we'll get I j over 2 sigma 1 y sigma 2 z is sigma 1 z sigma 2 y, and from this we infer that there are some matrix elements of the effective Hamiltonian between different Pauli strings. In this case, the first Pauli string is yz, and the second Pauli string is zy, and basically we have the Pauli string 0x connected by the effective Hamiltonian to yz and zx with the matrix elements I j over 2 and minus I j over 2.
Zy right.
Zy, yeah. So there is an effective Hamiltonian that changes one operator to another operator using the Heisenberg evolution. But we're expanding A of 0, which is constant. And to make it constant, we should evolve the corresponding coefficient function, a wave function, such that it is actually constant. And the evolution equation is it's minus I and this is just the Schrödinger equation. given graph. So, in general, there is a graph that includes various bit strings. And with two spins, there can be one bit string 0, 0, 0 Pauli string, and 0x, x0, 0y, y0, 0z, z0. So there are Pauli strings of weight 1, weight 0, and there are also Pauli strings of weight 2. And they are somehow connected. One important point is that 0, 0 is isolated. It can use this everything, so it's not connected to any other state. But such states are connected. Like 0x is connected to yz and z1, according to this diagram. So we have some graph with Pauli strings of different weights, and we have some quantum propagation of that graph. And in the end, we want to compute something like A of 0 and that is just the expectation value of d of t and c of t applied on the left and on the right respectively. Or actually, this is applied. This will be applied on the left, and this will be applied on the right. So this is an abstract expression, but what we should do here, we should expand A like this, and B, it's B there. B is expressed in a similar way, and then we should collect various terms, and the terms are those Pauli equations, or products of Pauli equations. And suppose that C equals sigma 1x, and or Z, and D equals also sigma 1z. And A has an expression like this. Then CL of T A of 0, CR of T the sum over A psi A of T sigma 1z sigma A of T of T. Everything depends on T. Sigma Z of T. Since the time argument is the same, it doesn't actually matter. We can drop T, okay? Because the algebraic relations between operators do not depend on T. So now we have some Pauli string sigma A and we're multiplying it by sigma 1z and sigma 1z on the left and on the right. And then we are taking the trace in this expression with B dagger for B. The point is that this looks like some operator that acts at the first position. And it acts in the space of operators. So here we have a wave function. The top line is a superposition of different Pauli strings. And we're measuring the presence of a non-trivial Pauli operator at the first position, essentially. We can play with C and D, and we can do different types of Pauli measurement. But all those measurements can be done on a given spin. So we have access to a particular position, and we can see whether it's a trivial label or a non-trivial label at that position. So we have a process where the wave function propagates on the graph. We can run this process, and then at time t, we do a measurement. And we detect the presence of some non-trivial or trivial operator at a given position. That's what we can do using our talks. Now, I would like to show you a qualitative picture of this propagation on the tree. It's a quantum process. It's a Schrödinger equation. However, in most cases, since we're at high temperature, interference is not important. Quantum interference, or quantum nature of our talks becomes important at low temperature. And that's the purpose of SYK and similar models in this study of our talks. If we're interested in the high temperature regime, interference is quantitatively important. We cannot completely ignore it, but we can replace the model by a different type of model where the Hamiltonian is not only spatially dependent, but also time dependent, and it's random in time. And then the interference will be gone. Qualitatively, at high temperature, interference is not important, and we have diffusive propagation along the tree. And we start somewhere in the bottom. This operator A includes just one Pauli string at time 0. So it is this. And then everything is spreading. And this spreading process is very similar to the growth of a bacterial colony. So suppose this A has some general form. Let me put it X, 0, 0, Y, Z, 0, 0, 0, another X. Let's just imagine that there are locations, some cells where we can put a dot. The dot corresponds to a non-trivial power operator. And let's look at this process. This process says that x, 0, comma x can go to yz or zy. So as the result of this diffusion on the tree, let me put another cell here with 0. You look at this place, this x can become yz or it can become zy. So we can have a process that takes this part of the picture to y comma z, and this part of the picture to z comma y. And that is similar to the division of this bacteria. This bacteria that is present in one cell becomes 2 bacteria. And that is again 2 bacteria. And it can divide, but when there is also a reverse process. When 2 go to 1, and we may interpret it as the result of overcrowdedness. Then there is not enough nutrients, and one of those bacteria die. And this is a very good analogy, actually. If we ignore interference, it describes qualitatively almost everything you can do with a tox. You can describe the propagation of a tox along a line if you consider something like this expression only has times, but we can also put spatial positions. Let this be at spatial position 0 in a spin chain, and that be at a spatial position j. Again, 0 and j. This means that we initially place a bacteria at position 0 and let it divide, and later on at time t we'll measure its presence at position j. And there will be some random process. It's a non-trivial process because it's correlated. Although there is no interference, there are correlations. And some of these guys may die, so there may be a configuration like this. Nothing here, and there are some poly labels, non-trivial poly labels, like Z and Y, and nothing here. And here it can be Z again, something like that. So this thing will grow grow until it reaches point J, and one can make two predictions immediately. Then on the average, it will grow with a constant speed, not diffusively. Yes?
Question. You mentioned the process of the tree.
Yeah.
What could we imagine as a branching number of this tree? What determines it?
The branching number depends on the number of bacteria cells present. The branching number is proportional to the number of cells. And if there are no bacteria, then the branching number is 0. If there is one cell, then the branching number is of the order of 1, and so on.
But it means branching number is not constant.
No, it's not constant. It's proportional to the number of cells present. And this is why interference is not important. There is a strong tendency to increase the weight of the Pauli string. It means that bacteria, if they are given free space, they will grow. They will multiply. And this tendency overcomes any subtle quantum effects in general. There won't be time for non-trivial interference because the wave packet will move in a certain direction. No time for forming complex patterns. But one can make various predictions. One prediction is that the friend propagates linearly forward. And another prediction is that it fluctuates because everything depends on the theory person who is on the front. It doesn't matter, or almost doesn't matter, what happens behind, because this space will be filled eventually. And the speed at which this guy runs can fluctuate slightly. And that results in the broadening of the front if we average over various realizations. I'm not talking about that, and maybe Professor Prozen will talk about some similar things. I'm not sure, but this is a model of chaos at high temperatures, and of course it's chaos. It neglects examples like the original Heisenberg chain, which is integrable. Integrability may alter those conclusions, but for a generic system, it's similar to the bacteria growth process. And next time I'll talk about the SYK, which is non-trivial at 0 temperature. And, it shows behavior that is not exactly similar to this.
Isn't it correct to say that what we described by now is a way to describe chaos in quantum system by means of some classical rate equation?
Yeah. Exactly. Okay, that's it for today. Thank you for your attention.